just like a thermostat. So, and what will that do is then that you bring an alarm signal through that. And as soon as that makes, it goes back to the controller, lights the light, alarm, dirty filter. And that's your dirty filter condition. Are you kind of with me? Yeah. Okay. So, now we've brought in the air, we came through our damper, which is for opening and closing to isolate this thing from outside, to stop the cold air coming in and the warm air going out. We've done some heat recovery, we've transferred the heat from the air going out to the heat coming in, air coming in. We've had our hot water of whatever temperature. Now, if I know the temperature here that I want coming in, say, and I know the temperature out there, I can do like we did last week, Q equals MC delta T, the CP for air being 1.02, yeah, right? Now I got my Q, I know now my Q, my number of kilowatts of heating that I need. I can now do Q equals MCP delta T and solve for M on the water side, using CP of 4.2 for the water, and tell me how many litres per second. This is what I was at last week. And then once I know how many litres per second, I know the size of my pipe, and I know all this stuff, right? So that solves all that. Same equation. All these services engineers who try to tell you that there's anything more than Q equals MCP delta T.
See, whatever's supplying that with heat, for example,
the boiler, yeah.
Is that hooked up to the boiler? How is that telling us to bring in water or whatever?
There's the valve. No, the water is set.
Right.
To always have a flow temperature of 70 degrees. That's what, like the boiler you have at home.
Okay. Yeah.
Right, so that's always putting out the water at the standard temperature. The only thing that happens then is that the valve, either 2-port or 3-port, opens or closes to take the water when it needs it. Okay. Now, if this is doing enough heating, if this is transferring enough heat, this doesn't have to do anything, right? Because it won't. What it does is, the way these work, when it's calling for heating, it normally, say it puts out, if it doesn't need any heating, it puts out 0 volts, right? No signal out. And if you talk about 0 to 100% heating requirement, well, the way to kind of do these in the controls is to talk 0 to 200%. And what they say is the 0 to 100% as it requires it, speeds up or slows down this wheel. That's the same as increases the amount of heat being recovered to control the temperature. And then once this is flat out and it's still not meeting the temperature you need, it starts opening the valve next. So it always recovers the heat before it starts using the boiler temperature, right? Which is only common sense. But you'd be amazed the amount of people who don't apply common sense when they're doing things. So now we've done some heating. Exactly the same thing for cooling. So this is our cold water going through, right? So this is just cold water flowing through this. Valve, same deal. And instead of coming from a boiler, it's coming from a chiller, right? And a chiller, this heat pump here, actually, what I was thinking, this heat pump here, this is a heat pump which takes the heat from the air and puts it into the water. This can run reverse cycle as well, as this can produce cold water by dumping the heat out into the air through the coil, right? You know, we did heat pumps before, and we said that if you're running backwards it's a chiller, and if you're running forwards it's a heat pump, right? So the thing is that on this side, here, we could have warmer water coming back from that, going through, evaporation happening here, cooling it down, condensing happening here, cooling it down, going back there, in here, right? And then, so we have our evaporation happening at the water side, and we turn it into a chiller. So the water comes out, okay, either this, or one that looks a way bigger. But the idea is effectively the same. It's a fridge unit, right? Only the size of it will change and what it will look like. But you'll normally have, we'll look at some of them again, but that's kind of what it's going to look like. So we have cold water. So instead of coming from a boiler for hot water, we just have a chiller producing cold water, probably at 6 or 7 degrees or something like that. Generally. Unless you want to do, okay, we look at some low energy other ways of doing things. Some people decide that they actually drill a hole in the ground and take up cold water and use that cold water to do it, to do the cooling, and use the groundwater for a heat pump to generate the hot water for the heating. Alright? And you can do creative things like that if you have the right geological conditions underneath the ground. Genzyme Watford did that in a more recent job. So that's our heating, and this is our cooling. And see here in the bottom, there's this tray to catch any condensate that runs down. And underneath there, then there's just you'd have a trap underneath, and it'll be piped away to a drain, right? So can you see there's kind of like just a connection like on the bottom of the sink. And here's our fan for our supply. And that blows the air out this one and up and out through whatever we want to supply into our room. And then on the return, we just want to put it into the system phase, we just suck the return back in here. It can be sucked from a duct anywhere. But return is crucial because you can suck return nearly from anywhere in a big room. Because you're not worried about, once you get the fresh air and the conditioned air out there where you want it, you can suck it back up one corner, no problem. So that's most industrial applications. Other than clean rooms, you're not really that worried about where you suck back the air from. Right? So, on the return side, it's coming back the way. We have a filter on the return to get any dirt that may have been generated in the occupied space or dust, and to protect this thing getting dirty. Now, this doesn't get that dirty, it's kind of self-cleaning as well. It doesn't really need that high level. Because say if dirt came in here, right? Say if dirt came in here and stuck to it here. Right? It got sucked in from outside and it stuck to it there. Well, as soon as the roof comes up here, the air is going that way through it next and it blows it off without the outside again. So it actually has kind of a self-cleaning effect. See? So on the bottom half the air is going that way, the top half is blowing it back out again. See, there's a controller here. This controller then does all sorts of stuff. And it's got a rotation monitor. There's a little motor here that turns it, see? So that's all that turns it. So for the one that I put in that was 5 meters diameter, it has a 0.75 kilowatt motor, which is small. Yeah. But as you can see, they're really easy to turn, right? That's all that does it. And but there's also a rotation sensor in here that measures to verify that the belt isn't broke.
That would be done as fast.
Maximum 10 revs per minute, kind of. Right. Maximum goes around once every 6 seconds. Now the other thing is, so that tells you that this yoke here, this controller here, is a stepper motor that's on most of these. Right? You didn't do stepper motors, did you?
That's necessary, is it?
No, very. So as I said, the first thing it does is it starts revving up. Some of them are set speed, right? But it's variable speed. So the first thing it does is it starts to rev up this, right? To speed it up until that's going full speed. And if that's still not enough heat can recover from that running at full speed, then do the rest of it, right? Open your valve and do the rest of your heating. Okay? So on the way back, it comes back, comes through the filter, through that, gives up its heat into there, and the fan blows it outside, outside. And that's it.
There would always be another duct then taking
the air
back
from the room into the unit, normally connected there, just that we're stuck for space. Yeah. So you have no able to supply and return to a room. And
that would be the one that's piped at the low level.
In clean room, that's the one that's sucking it back at low level from the clean room. Yeah. Yeah, the low level returns. Right. So that's kind of the basics. Now some of the stuff that's on this. This is the controller, like you tend to see any controller. So you did some controls, I take it, somewhere along the way. So on controls, the controller has inputs and outputs. Yeah? So signals going in and signals going out. That's really it. There's only two different types of signals there. They're either switches, just a switch going in like an alarm switch, a pressure switch, or someone switches a switch, which are digital inputs. They're either on or off, ones or zeros, digital. Or they're switching something on or off, 1 or 0, a digital output, telling something to come on or stay off. Or say that alarm condition or not alarm condition, or light alarm light or not a light alarm light, whatever, right? So they're digital outputs. So you only have two types of digitals in, which are switches going in, digitals out, which are switches going out, on or off, yes or no, 1s or 0s. And analog inputs and outputs. And analog signals are signals that are varying. You've done this somewhere along the line, I take it. So an analog, what would be an analog signal? You have normally time actually goes in. Time. It normally goes in as a pulse digital and you count the pulses.
Feedback from the motor.
Voltage would be one. Temperature would be another one that's constantly varying. You'll see a graph of it like this. It's not either. Humidity would be another one.
Speed of the motors.
Speed of the motor. So output, then digital outputs. What would it be? Why would we need a digital or an analog output? Why would you need one of them? To control something. Actuator gets a 0 to 10 volt signal to position it. It either needs fully open, half open, quarter open, whatever. Right? The speed of the fan. It'll be full speed, or half speed, or quarter speed, or whatever. They're analog, constantly varying signals. And normally, these analog signals are either currents or voltages. Right? So normally, you'd have something like 4 to 20 milliamps, or 0 to 10 volts. And for most of this stuff, it's 0 to 10 volts. Right? Or 2 to 10 volts, some of them are. So, but 0 to 10 most. And if you had a 0 to 10 volt and you wanted to turn it into 4 to 20 milliamp signal, what would you do? For all the electricians in the house. So, if I had a 0 to 10 volt signal coming out and I had something that needed a 4 to 20 milliamp signal, what would you have to do to the signal to make it work? How would you convert it? A resistor. Yeah. Yeah, you just put a resistor across it. 10 kilo ohm, I think, is what you need. And that'll do the trick. Right, if you do your equals V equals IR. Just to solve that equation, you change it. So, and what it is, 4 milliamp is 2 volts. Right? It's 20. It's one of them anyway. But you can do it just by putting a resistor across it. All you have to do is put a resistor across the terminals and that'll change the signal. So by the way, just to know that there's something that you can do if it's wrong. You don't have to remember what it is, you can go and look it up. But just to say that if you have voltages and current signals, that you can actually change them by just sticking a resistor in. You don't really remember which one it is, you can do the sum. So outputs, analog outputs can be voltages or currents generally, right? Voltage, 0 to 10 volts, 0 volt means that nothing going to the valve, 10 volts means that it's getting a signal. The symbol for the signal is normally Y. On any of these sorts of things for valves, Y is normally the signal. So you normally see 3 wires going to these things. Any come across these? You'll have G, GO, and Y. Have you come across those letters? I don't know if they're on this. There's Y and U, and okay, they're symbols. You can read them on this properly. But so G is normally your 24 volt power to power your motor. GO is normally your negative, and Y is your signal. Your signal coming to this, so Y. And then you can have a signal coming out to say what position it's actually at using limit switches and stuff. But I'll get into that sort of stuff if we need. But so the point is that on your heating or your cooling, heating is only going to change the dry bulb temperature. It won't change the amount of moisture. We have no condensation or no evaporation happening under normal conditions, right? Hot water flowing through the coil. The relative humidity of the air will change. The actual amount of moisture that the air can change. What happens as it gets warmer? How much moisture can it hold? It can hold more. So we talked about this ability for air to hold more moisture when it's warm. Where do we see that being put into practice? What systems are in place to allow air to absorb more moisture? What sort of machines do we ever see that are designed to heat the air so that it'll absorb more moisture? Huh? No. What sort of a machine have you ever seen that was specifically designed so that it would heat up the air so that the air could absorb more moisture? Huh? clothes dryer, hair dryer, hand dryer, all those things, hot air. That's why the air is warm, because the air can absorb a lot more moisture. If we look at the curve, we say this relative humidity. The relative humidity we talk about was the actual amount of humidity versus the total amount of temperature that temperature.
So,